So here we are in part 4 of kinetics. This is our last day in kinetics. So I hope that you guys are following along. I hope that you're working through the problems. I hope that you're able to attend the Zoom meetings, because really applying all these concepts and working through the calculations is really where this is going to kind of sink in for you. So just to review the last time we met together, we had introduced a couple of things. So we had talked about the integrated rate laws. We talked about the various ways that we could plot this theta to get the rate constant. So the slope is going to be the rate constant, it's either a negative slope or a positive slope. And we talked about half-lives, which is the amount of time that it takes for the concentration of your reactant to drop by half. And you don't always have to start from 0. Each half-life, depending upon your reaction order, is different. You can use your half-life to determine your reaction order as well. So if you see that your half-life is getting shorter over the course of that reaction, then that's going to tell you your 0 order. If your half-life is independent, so it stays the same, so as your reaction goes, your half-life doesn't change, then you're first order. And if your half-life gets longer, then you're going to be second order. So half-lives are important. We also talked about looking at the effect of temperature on the rate of a chemical reaction, and the only equation that allows us to factor in temperature is this Arrhenius equation here. And so here's your temperature component. And this also introduces this term activation energy, which is this barrier, this energy barrier to get from your reactants to your product for your reaction to happen. So you have to initially pay an energy penalty, and then you get energy out on the backside of that. And so this activation energy, the higher this activation energy is, the slower your reaction rate is going to be, because the more energy that you have to overcome to get to products. So today we're going to build on this. We're going to talk about reaction mechanisms. And so the reason that you can't apply stoichiometry in kinetics is that very few reactions happen in a single step. If a reaction happens in a single step, then stoichiometry applies, but reactions often happen in multiple steps. You may not see those individual steps written out because you're just going to look at the overall chemical reaction, but there was probably multiple steps that had to happen along the way. So we're going to propose this thing called reaction mechanism, which is looking at these individual steps for chemical reaction and understanding how they're going to affect the overall rate. If we have the individual steps, then we can determine the overall rate of the reaction fairly easy. What we have to know is, do the individual steps happen fast or do they happen slow? We're also going to talk about molecularity, and this really applies to these individual steps of the reaction. And then we're going to lastly kind of touch on catalysts, and catalysts can affect the rate of a reaction significantly as well. So reaction mechanism is the mechanism by which your overall reaction happens. And so you might have 2 steps. Your reaction mechanism would be step 1 and then step 2, and you would add those together to get your overall chemical reaction. And one thing to think, if you see a chemical reaction where you have 3 reactants, you're going to have a multiple step reaction happening, because the chances of a single step with 3 reactants is very low, because you would have to have all 3 of those reactants to collide together in the right orientation with enough energy to go overcome the activation barrier for that reaction to happen. So anytime that I see a chemical reaction written where I have 3 reactants, and I know automatically that that's going to be a multi-step reaction. In collision theory, the chances of those 2 things colliding at the same time is going to be really small, if you think about it. Okay, so reaction mechanisms. They allow us to describe the series of reactions. We're going to start simple. Let's say I have hydrogen gas reacting with iodine monochloride, and I go to form HCl gas and I2. So this would be my overall reaction. If I was going to write my rate law for this, it would look like this. Rate equals my rate constant times hydrogen to some reaction order and ICl to some reaction order. And I'm not going to use stoichiometry. Remember, I'm going to determine these reaction orders. I would need experimental data to determine N or M, but I could also find it if I had my individual steps. So I could determine my reaction order using experimental data. I could look at my method of initial rates. So that was back in, I think, part 2. I could graphically analyze concentration versus time, and we could determine first, second, or zero order, whichever one gives you a straight line, by plotting natural log of concentration versus time, 1 over the concentration versus time, or concentration versus time. And so whichever one of those is going to give you a straight line, that will tell you your reaction order. I could compare half-lives, but I need time and concentration values. So you could do any number of these to determine the reaction order. I could also look at my reaction mechanisms. So these we've already discussed. This is what we're going to cover today. So if I have this simple reaction here, it occurs in 2 steps. Step 1 happens, I take hydrogen gas, I react with 1 iodine monochloride gas, and I form HI plus HCl. So that would be my step 1. Step 2, I take my HI that I formed up here, and I react that with another ICl, and then I form HCl plus I2. So these would be my 2 steps. So I should be able to add these together and get my overall reaction. This guy up here. So I should be able to add these 2 together and end up with this one. So I'm going to do that by taking everything that's on the reactant side. I'm going to write it down. It's ICl plus HI plus ICl. So that's all of my reactants here. And I'm going to write all of my products. HI plus HCl plus HCl plus I2. Then I'm going to look to see if there's things on both sides that will cancel out. So here I have HI on both sides, so I'll cancel that out, and then I'm going to add these together. So I'm going to end up with H2 plus 2 ICl goes to 2 HCl plus I2. And then if I did this right, this will equal my overall reaction. So these are viable steps because they sum up to my overall reaction. So let's define what's happening here. HI, I was able to cancel out because it's produced here and then it's used up here. So it's produced in the first step and reacted in the second step. That makes it a intermediate. This is going to be a substance that is produced, then reacted in a set of reactions. So it doesn't show up at all in the overall reaction. So if you didn't have these individual steps here, you would never know that HI was actually part of this process, that it's produced in step 1 and then consumed in step 2. And so that's the definition of an intermediate. An intermediate is produced, then consumed. In intermediates, we can usually, when we get to the overall reaction, they're going to cancel each other out because I'll have them on the reactant side and the product side because they're produced and reacted. So they cancel each other out. So you never actually see them in the overall reaction. All right, so this would be an example of a set of steps for an overall chemical reaction. And looking at intermediates, so I'm going to rewrite my 2 steps here on a separate sheet of paper so that I have them. And we're going to look at how we can determine the overall rate of the reaction if I know just a little bit more about these individual steps. Now I'm going to tell you that step 1 happens fast and step 2 happens slow. If step 2 is really slow, what that means is that if this is fast, this is going to limit the rate of the reaction because it's the slow step. So we call it the rate limiting step, whatever your slow step is. If this is fast, this is going to be an equilibrium. So this becomes an equilibrium scenario because if this is my fast step, then I'm going to quickly form HI and HCl. This is going to be hanging around waiting on this slow step here. So it has the opportunity to also go back to hydrogen gas and ICl. And if this is my fast step, then this is going to be in equilibrium. So I'm going to automatically assume that my fast step before that precedes a slow step is going to reach some sort of equilibrium because this HI isn't being used up fast enough for it to not. So then this means that my slow step is going to limit the rate of that reaction. Let's look at another reaction. NO2 plus CO. So this would be my overall reaction. I have nitrogen dioxide reacting with carbon monoxide, producing nitrogen monoxide and carbon dioxide gas. Let's see, these are my steps. So I have step 1, NO2 reacts with another NO2 to form NO3 and NO. And step 2 happens when NO3 reacts with CO, form NO2 plus CO2. So first off, let's add these up to make sure that they're going to equal my overall reaction. So I'm going to write all my reactants here. NO2 plus NO2 plus NO3 plus CO goes to NO3 plus NO plus NO2 plus CO2. Do I have any intermediates here? Things that are produced and then consumed. So this is produced and then it's consumed, so NO3 is my intermediate. And my overall reaction would be 2 NO2s plus CO goes to NO. But I have another NO2 here that I can remove. Going to have an overall reaction of NO2 plus CO, NO plus CO2. So that's my overall reaction. So let's say step 1 is slow. Let's say this is my slow step and this is my fast step. If this is my slow step, this is going to be my rate limiting, meaning that this step is going to take a lot of time. Once these get produced, then they quickly react to form my products. This is going to determine the rate. What do you notice about the reactant that's in this slow step? It's only NO2. So if this is my slow step, I'm going to write out a rate law for this. So my rate law for this slow step would be K times NO2. Now I'm going to take into account stoichiometry. So I'm just going to write an individual rate law for this. Allow my reaction order to equal the stoichiometry here. And I can do this with these individual steps. This would have a rate equal to K times NO3 times CO. And these would both be first order. But this doesn't matter because this is fast. This is not going to control the rate of the reaction. This is the only step that's controlling the rate of the reaction. So my overall rate law for this equation is rate equal K NO2 to the second. So second order in NO2. If step 2 is slow, then it gets a little bit more complicated if my second step is slow. If I were going to draw an energy diagram for this, because each one of these is an individual step, I'm going to have 2 activation energies. I'm going to have an activation energy for step 1, and I'm going to have an activation energy for step 2. But since this is fast, that tells me that this activation energy here is going to be really small. This is going to be my larger activation energy. So if I were going to draw what this looked like on an energy diagram, I would have, this would be my reactants, this would be my products. So this is an exothermic reaction. My products have lower amount of energy than my reactants. My first step would be, this is my slow step, this is going to have a high activation energy. This is going to be my intermediates. This is where I'm going to produce NO3 and NO. And then my second, so this is EA1, and that is the energy it took to get from where my reactants were on the energy scale to the very top of that peak for my activation energy. This is the slow step. My second step might look something like this, where now my activation energy, EA2, is much lower than EA1. And then I'm going to go down and produce my products. And so my delta H would just be the difference from where my reactant started and my products ended, but my activation energy is from where my reactants are to the top of this energy barrier. So this is step 1, reaction 1. This is step 2, reaction 2. My second reaction is going to go much faster because the activation energy is much lower. So if I propose this reaction mechanism, it has to be valid. So for any proposed reaction mechanism, you have to be able to validate it. And the 2 ways that you can validate it is the sum of your individual reactions equal the overall reaction, and that the rate law predicted equal the experimental rate law. So it's consistent with the observations that you have. So if I have an initial slow step, it's really easy because I can just look at what's happening in that first chemical reaction and go from there. If I have a step that's slow, that's anything other than the first step, now it starts to get a little bit more difficult. So let's consider a scenario where I have a reaction where my first step isn't fast, my first step isn't slow. So here I have hydrogen gas reacting with nitrogen monoxide to form water and nitrogen gas. And this occurs in 3 steps. So this is a 3-step mechanism. Step 1 happens when I have two NO gas molecules going into O2. So basically they combine together. This step is fast. So that means that it's going forward, but it's also going in backwards. So I have equilibrium. So my first step, this is happening and it's going to reach some equilibrium and then it waits. It waits for this product here to be consumed in the next step. My next step takes hydrogen gas and reacts it with my product from step 1 to form water plus N2O, dinitrogen monoxide. And this is slow. So this is going to be rate limiting, my slow step. And then my step 3, I'm going to take N2O, I'm going to react that with another hydrogen gas, and I'm going to produce nitrogen gas plus water. And this is also fast. So this is not going to reach equilibrium because it's just going to be fast, and then your reaction is going to end. It's going to use it all up. So to validate it, I'm going to make sure I sum up my individual reactions to equal my overall reaction. So if I sum these guys up, I'm going to have 2NO plus H2 plus N2O2 plus N2O plus H2. So those are all my reactants. I just took all of these and added them together. All my products, N2O2 plus H2O plus N2O plus N2 plus H2O. Now I'm going to cancel out my intermediates. So where are my intermediates? This is an intermediate because it's produced and then consumed. And then this is an intermediate because it's produced and then consumed. So I can cancel these two out from my reactant side and my product side. And then my overall reaction is 2NO plus 2H2 goes to 2 waters plus N2, which is consistent with my overall reaction. So I'm validated by step 1. Now I need to find my overall rate of the reaction. I can write a rate law for each of these. I can say this rate law here for this individual step is K times NO to the second. So I'm using my stoichiometry here. I'm just looking at my reactants. I'm going to use my stoichiometry to write my rate laws for my individual steps. This rate law here is K times H2 into O2. And then my rate law here is K into OH2. Of these, this one doesn't count because it's fast. This is not going to affect the overall rate of the reaction. This is my rate that's going to affect the overall reaction because that's my slow step, that's my rate limiting step. So if I pull that guy down here and I say, all right, I have this chemical reaction, this is my overall reaction here, and this is my rate law based on the slow step up here. That means my rate equals K times the initial concentration of hydrogen and the concentration of N2O2. But what do you see up here? This is not a reactant in the overall equation, so I can't leave it in the rate law. So I have to get rid of N2O2. Can I just delete it? I can't. But what I know about N2O2 is going to come from up here, because if this is in equilibrium, let's say I have a rate constant going forward and a rate constant going in reverse. If this is in equilibrium, then K1 equals K2. Because my forward rate is going to equal my reverse rate. This is going to reach equilibrium. It's going to wait for this to be, every time one of these is moved down to here and gets reacted, then it shifts the equilibrium. And so I have this equilibrium scenario. I can use that to get rid of this guy. So I'm going to take this rate here. This is my rate forward. I'm going to write a second rate for my rate backwards. K2 is into O2 because this is my rate going backwards. This is my rate going forward. This is my rate going backwards. At equilibrium, these two are equal to each other. So I can write them down here. Because my overall goal is I want to get rid of this N2O2. By setting these two equal to each other, I'm going to be able to do that. So K1 NO squared equals K2 into O2. Since K1 equals K2, these can fall out. And then that allows this equation here. So NO squared equals one of these. So I can take this guy and use this into here and substitute in for my intermediate. So that would give me my overall rate law now equals KH2, which I haven't messed with because that's the same. And now instead of N2O2, I'm going to substitute in NO to the second power. So this would be my overall rate law. And then I would have to experimentally test this to tell if it equals my experimental rate law. But if these are the steps that happen and these are right, that this is fast, this is slow, then this is going to limit the reaction and this is going to be my rate law. That's how we can use reaction mechanisms to determine our overall rate law for a reaction as well. So molecularity deals with how many reactants you have in your individual steps. So this has one reactant, so my molecularity for that step would be 1. We would call that unimolecular. Here I have 2, so this would be bimolecular. If I had 3, then it would be termolecular. So, and remember, anything where you have over 3 reactants is very unlikely. Even actually 3 reactants is unlikely. So most of your individual steps are going to be unimolecular or bimolecular. So this would be kind of your elementary steps. So these are these individual steps. So I can use molecularity to also describe that step. I have a unimolecularity step, I have a bimolecularity, I have a termolecularity. You can think of this slow step as a traffic jam on the freeway. If everything's whizzing along, you know, you're in that fast lane, you're moving, but all it takes is some little hiccup and then everything starts to get backed up. It's that slow step is the backing up of that process. And so you can have concentrations of your reactants that are from a earlier, faster step, and they just start to build up until they're used in the second step. Because if this is going really slow, that means it has a high activation barrier. And so you're having to overcome that activation barrier to get to the products. And so the accumulation of N2O2 starts to build up over time. All right, so catalysts. Catalysts are great, and they're used a lot in industry to affect the rate of a reaction. So a catalyst is another way to increase the rate of a reaction by lowering the activation energy. Catalysts can be used and produced in a chemical reaction. They're not an intermediate, or they can just sterically aid in a chemical reaction. So they don't have to actually be part of the chemical reaction, but they also can be. In all cases, they increase the rate of a reaction by lowering the activation energy of the slow step, that rate limiting step. So if we look at ozone, if ozone is left, this reaction here occurs. So ozone will produce oxygen. My overall rate law for this is K times O3 to O2 minus 1. It occurs in 2 steps. Step 1 happens when one ozone molecule produces O2 plus a single oxygen, and this is fast. This happens fast. So my rate law for this would be K times O3, ozone. Step 2 is slow, so step 2 happens when another ozone molecule reacts with that single oxygen to form O2 gas. This is my slow step. So my rate here would be equal to KO3 O. And O is an intermediate. When I add up these and I write my overall reaction, I have 2O3 plus O goes to 3O2 plus O, and O is my intermediate, so I'm going to remove that from both sides of the equation. If this is fast, this is an equilibrium, so that means that my rate of KO3 equals K times O2 times O, because I'm looking at this one going forward and this one going in reverse. So this is my forward, this is my reverse, these two. So I can substitute in O here in my slow step for this. I can rearrange this to get O by itself. So first off, these K's come out. So that means I'm going to take O3 and divide it by O2, and that's going to give me O. So I'm going to plug this into this equation to get a rate law that deals with my initial starting, which in this is going to be O3. And then I'm also going to have in my rate constant O2, which is a product. I have both in there. So this is a little bit more complex of a rate law. So this would be my overall rate law, which is not optimal because I have a product in here. If I were to look at the energy that's happening here. I'm just going to draw an energy diagram. And this would happen normally when you have ozone. So step 1 is fast. What we'll do step 1. This goes to O2 plus O. And then step 2 would be that O is reacting with O3. So that'll be my step. So this is my reactants. Step 1, my reactants. Step 2, and then my product here is going to be 2O2. O2 plus O2. This first step is fast. So this is going to have a relatively low activation energy. So this is my activation energy for step 1. Step 2, this is my slow. So it's going to have a higher activation energy. So this activation energy here, EA2, is much higher. Higher because this is my slow step. All right, so this would be what would happen. This is an energy, and this is my reaction as it progresses. So it's 2 steps, so I expect to see 2 activation energies, one for each of these steps. This is step 1, this is step 2. I would expect if step 2 is my slow step for it to have a higher activation energy. Now if I add a catalyst, let's say I take this reaction and I add a catalyst. And chlorine is a catalyst for this reaction. So those fluorochlorides that are polluting our atmosphere help this reaction along. This would be step 1. Step 2 looks like this. ClO plus O goes to Cl plus O2. It's a very different set of conditions that are happening now. Instead of O3 breaking into O2 and O, this is your fast step, and then waiting for another ozone molecule to react with this oxygen. Now I have O3 reacting with chlorine to form this intermediate here. Then that intermediate is used up in the next step to form O2. So this is my intermediate because it's produced and then consumed. This is my catalyst because it's used and then produced. So this is my catalyst. So an intermediate is something that's produced as part of a step and then used in subsequent steps, whereas a catalyst is something that's there all along. It may not be written in the overall reaction because it's consumed and then it's produced, so it effectively cancels out. So if I add these together, I'm going to get the same overall reaction. So here I'm going to cancel out my intermediates. I'm going to cancel out my catalyst, and then I get my same overall reaction for step 2. So this is step 2, but now it's broken into 2 steps. So my overall reaction for step 2 was O3 plus O goes to O2 plus O2. This was step 2. If I look back to here, this was step 2. So now that catalyst has added another step. We'll call this 2A and 2B. So I've taken step 2 and now I've moved it into 2 additional steps. But what that did is it lowered the activation energy for each of those steps. So by adding in chlorine, my activation energy now looks like this. This would be step 2A and 2B. My activation energy is much lower. Even if I add these 2 together, it's still going to be much lower than that initial activation energy for that step without the chlorine. So chlorine catalyzed step 2, which was the rate limiting step. It reduced the activation energy and it will increase the rate of the reaction. So having chlorine present when you have ozone present, it speeds up the degradation of ozone into oxygen gas. And so that is happening in our outer atmosphere where we have a lot of ozone and we start to have these holes in the ozone layer because we're interjecting chlorine gas into the atmosphere, and that's going to catalyze this reaction and make this happen much, much faster than it normally would. These are called transition states, by the way. These here are called transition states. This one too, because they're individual steps that lead to that overall reaction. We're just going to talk about briefly, really quickly, about the different types of catalysts that are out there. We have homogeneous catalysts, which are going to be in the same phase as the reactant particles. So if all my reactants are in a gas, a homogeneous catalyst would be something that is in the gas phase. Biological catalysts are used a lot in our body, and so if you take biochem or any kind of biology class, you're going to talk a lot about enzymes. Enzymes are a catalyst because they allow a molecule to bind to it, and it usually fits in like a specific way into the catalyst, and then that catalyst affects a change on that. So it's usually breaking things apart. Here's an example where you can take sucrose, and sucrose, your body will bind sucrose and then break it into glucose and fructose. And so your body uses glucose in metabolism. And I think that about ends it. So another type of catalyst is your catalytic converter, if you think about your car. So that's a solid phase metal. It's usually palladium. And it traps partially reacted products from combustion that are coming off of your engine and basically allows them to kind of absorbs them into the surface of the catalytic converter and then allows them to fully undergo combustion. And so that reduces the amount of partially reacted octane molecules and other things that are additives and stuff that are in your gas. And so that would be another example of a heterogeneous catalyst. All right, so that kind of ends our chapter. And so we will come back together. We will do some problems together in our live Zoom meetings, and then we'll come back together in pre-recorded lectures into the next chapter, which is going to be on equilibrium.